Good evening, all. So today I will continue the last week lecture. Mm. So in the last class, we discussed up to the point where we derived the wave equation for the electromagnetic waves. Okay. So we derived the wave equation for electromagnetic waves. So the wave equation was of the form Laplacian E equals mu E double squared E over double T squared. So this equation is known as the wave equation for the electric field. The same uh, sort of equation can be derived for the magnetic field. Okay, so the magnetic field we can derive the same equation, which will be like this, right? So this also can be derived using the Maxwell's equation, and we can use the same set of steps to derive this equation. So in today's class, we will be discussing about the uniform plane waves and the properties of uniform plane waves. Okay, so okay, so the Maxwell's laws, predict the existence of electromagnetic waves generated by varying currents and charges, time varying currents and charges. Okay, so such waves propagate with a finite velocity. In a uh, finite velocity and independent of the sources, that produce them. Okay, so what we mean by that is that although a certain source was used to generate the electromagnetic waves at a certain point uh, in the geographical area, let's say the antenna, an antenna is available at a certain location, and in this location the electromagnetic wave was generated, and after generating the initial um, magnetic field and magnetic field around the varying current conductor. Okay, so this is a varying current conductor. So after a certain initial magnetic field is created around a varying current conductor, due to the um, laws that were defined by, uh, for example, uh, the Faraday's law, the electric field is generated because of the magnetic field. Okay, so after that electric field is generated like this, due to the magnetic field, let's say this is the magnetic field which was created. Okay, so the magnetic field which was created, I will denote using B, and the corresponding electric field is generated because of the Faraday's laws and his theorem. However, the idea that this electric field can create another magnetic field independent of any source of uh, varying current or charges is what is uh, significant about the Maxwell's law. So, so after we initially create a certain electric field, right, using a magnetic field, then that electric field is able to generate another, I mean, magnetic field as a result. So the magnetic field and electric field can get generated mm, because of previous electric field or magnetic fields that were present in the area. So without any time varying uh, charges and currents, this uh, these electric field and magnetic fields can get generated. So that idea was given mainly by the Maxwell. So although um the Faraday's law and Ampere's law uh, told us about the generation of the electric field due to a varying magnetic field, and also, right, so when we vary the magnetic field, the electric field is generated around the magnetic field, um, around the magnetic field variation, and the electric potential is created in this direction. This was brought out by Faraday's law. However, like Maxwell made the connection that after you create this kind of electric field, that electric field itself can generate another loop of magnetic field without any kind of a source involved. So the electric field therefore can generate another magnetic field around it. So that magnetic field is generated in a certain manner such that it opposes the direction uh, that cause the electric field to get generated. So anyway, the electric field can generate uh, a magnetic field. So likewise, uh, the varying electric field is able to generate a varying magnetic field. With the help of the varying magnetic field, we can create another set of varying electric field components. So with the varying electric field components, we can generate another set of varying magnetic field components. So like that, it will go like in a chain event. It will happen like a chain. So over and over it happen, and it will generate a set of uh, electric field and magnetic field variations along a certain direction which is perpendicular to both the electric field and magnetic field variations. Okay, so this phenomena will generate a wave like this, a wave like this. a wave like this, right? Where the electric field component is varying with this kind of a manner. So the electric field components are varying with this kind of a manner, which means that electric field amplitude is or electric field is behaving like a wave, behaving like a wave. Its amplitude is varying according to its 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 uh, its uh, its displacement is varying according to a wave. Similarly, there's magnetic field that is getting generated, which is getting generated in the uh, perpendicular direction to the electric field, and it will be generated like this. So the magnetic field will be generated like this in the perpendicular direction. Okay, so I will draw the magnitude of the magnetic field like this at each point of the propagation, and the amplitude of the magnetic field will follow a wave-like behavior. So the magnetic field also is behaving like a wave, right? So that is what we discussed as the wave equation of the magnetic field, right? So this is what we derived as the wave equation of magnetic field, right? And the wave equation, we derive the wave equation for the electric field also. So with all that derivations, what we tried to do was we tried to show that electric field is behaving like a wave, right? So the wave equations were proving us that the electric field and the magnetic field is following a wave-like behavior. Okay, so that is basically the understanding related to electric field and magnetic field uh, 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 behavior in a uh, and its propagation in a certain medium. So afterwards, we are now going to find the properties of such kind of a wave. Okay, so we are going to find the properties of such kind of a wave. So the wave we are going to consider is the electromagnetic wave, and there are many types of electromagnetic waves. Okay, so the simplest type of electromagnetic wave is the uniform plane wave. Okay, so uniform plane wave is the simplest type of um, electromagnetic wave. So in order for us to uh, study the behavior of electromagnetic waves, we are going to study the behavior of the most simplest type of electromagnetic wave, right? So we can study the electromagnetic waves, right? So the basic type of electromagnetic wave is the uniform plane waves. So we study that to understand uh, the basic properties of an electromagnetic waves. So if we know the properties of the simplest type of electromagnetic wave, then we can find the properties of more complex electromagnetic waves. So the complex electromagnetic waves are basically made out of uniform plane waves, right? So complex type of electromagnetic waves complex electromagnetic waves are made up of superposition of uniform plane waves. Okay, So by the combination of uniform plane waves, complex uh, electromagnetic waves are getting generated. So in order to understand such kind of complex electromagnetic waves, we need to first focus on studying the uniform plane waves. So the uniform plane waves are special type of uh, electromagnetic waves. Okay, so uniform plane waves are special type of uh, electromagnetic waves. So the reason that I'm saying that is, now let's say we are generating an electromagnetic wave at a certain point in the space. So if we are generating our electromagnetic wave in this kind of a position in the space, so the amount of energy that is available in the near field is very high. The energy that is radiated from the source of electromagnetic waves, right? So in the near region where the electromagnetic wave is generated, we have high amount of energy. So the radiated energy is in the form of a sphere. And however, once we move along this, along a certain direction, once we move along a certain direction, we can observe that the energy of the radiation that is emitted from the source is getting uh, uh, like reduced, and the radiation is um, uh, I mean it can be seen to have uh, it can be seen to vary along a certain plane which has um, less curvature. Okay, so what I mean is, now let's say uh, there's a uh, we are measuring the energy around this source of electromagnetic waves at a near location. So if we measure the energy at this near region, or we call this near field region, we call this near field region. Once we measure the energy near the close by region, we see that there's like energy congested in the uh, like a sphere around the source. But once we move along the all the other directions, and in every other direction, we can see the energy that is emitted will be also in the form of a sphere. But now, once we observe the electromagnetic wave at each point in the sphere, right? Once we observe the electromagnetic wave that is received at a certain location, right, on the sphere, we can observe that the sphere surface is like a plane. Okay, once we move further and further away, right? So once the distance in here is very large, right? So the gap is very large, right? Large gap. So when the gap is very large, then the sphere and its curvature reduces. The the curvature of the sphere reduces, right? So the curvature of the radiation sphere reduces, right? reduces. And once we take a surface area of on this sphere, right? Once we take a small surface area on this sphere, let's say this is the surface area that we take from the sphere, that looks like a plane, right? So this small surface area, I mean, let's say this is a small surface area. What that small surface area look like a plane with less curvature. So the wave that is going through this plane is showing uh, characteristics, and the wave that is propagating like this is known as the uniform plane wave. Okay, so the 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 plane wave that is generated is known as the uh, this is known as the plane wave, and that plane wave is getting generated at the region uh, far field region with respect to the source of the electromagnetic wave. So these waves that are generated at a far field region, right? So at the far field region, the electromagnetic waves that are generated uh, can be observed as uniform plane waves, right? So these are uniform plane waves. So this is the simplest type of wave that is getting generated, uh, which is generated and which is observed to be propagating through a certain plane surface. So the reason that we say this is uniform plane wave is because the amplitude of the plane wave is constant. Its frequency is also constant. Okay, so you might wonder why these constants and parameters of the wave is constant. Okay, so uniform plane waves are basically considered uh, to be propagating in the free space. Okay, so the uniform plane waves propagate along the free space. So once it is propagating along the free space, its amplitude does not get attenuated. Its frequency does not get attenuated. So therefore, the amplitude remains the same. So, okay, so this is the behavior that uh, we will see if the plane wave is moving in a free space. Okay, so uniform plane waves are actually uh, like a theoretical idea. This is a theoretical concept, mainly because most of the time in the environment uh, we have the medium through which our electromagnetic wave is propagating. So because of that, the amplitude of the wave is getting attenuated, and the frequency can vary with different mediums. And likewise, some changes can happen in the wave properties once it is moving in a certain medium, right? However, in this section, we are going to consider uniform plane waves which are moving in a free space. And these uniform plane waves are mathematically, I mean, known to be theoretical because it might not exactly exist in the real world, right? However, the uniform plane waves are useful to study the most complex type of electromagnetic waves, as I said before, right? Because all those complex type of electromagnetic waves are superpositions of multiple uniform plane waves. Okay, I hope it is clear to you, and if it is not clear, please let me know. Okay, so I will inform to you regarding the mid exam at the end of today's class. So wait for that. If you have questions, you can let me know. Right? So I will write down regarding the uniform plane waves. The actual waves. The actual waves radiating from the sources are spherical, are radiating a spherical, um, it is, let's say, okay, the actual waves radiating from the sources are spherical. So the actual waves radiating from the sources are propagating um, in a spherical manner, but at large distances from sources. At large distances from sources, they become practically plane waves. Okay, so that is basically regarding the generation of plane waves. So let's talk about the properties of the uniform plane waves. Okay, so um, um, however, like let's first write down the uh, assumptions that we assume for the uh, the uniform plane waves and their generation. Okay, so we assume actually. Okay, so the uniform plane waves are propagating along a homogeneous lossless medium. Okay, so when we are studying uniform plane waves, we are making some assumptions. Okay, so those assumptions are so the first assumption is that both the electric field and magnetic field components or magnetic fields depend only on the z coordinates and time time. Okay, so what we mean is that the electric and magnetic fields do not vary, right? Do not vary along x and y directions. Okay, so we are considering a scenario where the wave that is getting propagated, okay, is composed of electric and magnetic fields, right? So those electric and magnetic fields do not uh, increase or decrease in amplitude along the x and y directions. Okay, so the amplitude of the electric field and the amplitude of the magnetic field remains the same along the xy plane. Okay, so if we take, right, if we take a situation where we have the xy plane here. Okay, the xy plane is here. The electric field and the magnetic field, which causes this wave, is having a certain amplitude, and the amplitude, let's say, is about this size. That amplitude, right? That amplitude does not vary along the x-axis, right? So now this is the xy plane. So xy plane has x-axis and y-axis, right? So if we take xy plane, the x-axis is along the x direction. This is the x-axis, right? And then this is the y-axis. Okay, so we are going to take the axis in this direction for this phenomena, and the z-axis is along this direction, and the wave is propagating along the z direction. Okay, so wave is propagating along the z direction. So the xy axis that we have on this plane, right, denote these directions, and the electric field and its amplitude does not vary along this direction. That means the magnitude of the or the amplitude of the electric field do not keep getting large. It's constant. It's constant along x-axis direction and also y-axis direction. There's no increase in the electric field amplitude, right? So if there is some kind of a increase in the electric field or magnetic field, then it must be a case where we produce some energy in between, right? It must be a scenario where we are providing energy to this wave, but we consider scenarios where we do not provide energy to the wave in an intermediate location between the transmission of the wave and reception of the wave, right? So in intermediate locations we do not provide electromagnetic force. Therefore, the amount of electric field amplitude and the magnetic field amplitude do not change along the xy directions. And also, the electric field or magnetic field do not increase its amplitude along the z axis, but the position of the electric field varies along the z axis, and it also varies with the time. So that is why electric field is known to be changing with the z and t. Similarly, the magnetic field is known to be varying with the z and t, mainly because the magnitude or amplitude of the electric field, the the value of the electric field varies with the position, right? With each position z value, right? So when we take the diagram here, there are different values of z that you can take. So for each value of z, we have different type of electric field amplitudes or magnitudes. So we have different values for electric field at each z direction, z point. And also depending on the time, the amplitude that we consider is also changing. Because of that, the based on the position and the time, the electric field value changes and magnetic field value also changes similarly. So that is what is given in the first assumption. The second assumption is that this electromagnetic wave that we are considering is propagating in a homogeneous and lossless medium. Okay, so the electric and magnetic fields exist in a homogeneous and lossless medium. Lossless medium with parameters epsilon and mu. Okay, so lossless means there's no attenuation. there's no attenuation on the wave's amplitude. Right? There's no attenuation in the wave's amplitude. Okay. However, the amplitude is determined based on the epsilon and mu, which are constant for the medium, right? So the as long as the medium does not change, the amplitude does not change. So the right, so we are considering a scenario where the wave is propagating in a constant medium, right? The medium does not change. So the wave is propagating in a certain medium, and the medium does not change. That medium has characteristics that are determined by the epsilon and mu parameters. So the medium is defined using these parameters. However, the medium is like assumed to be constant throughout, and it is homogeneous throughout. That means the composition is uniform throughout the uh, throughout the propagation. Composition is uniform throughout the space through which the wave is propagating. Okay, so I hope it is clear to you. So these are the two assumptions that we are using to analyze the behavior of uniform plane waves, right? So uniform plane waves that we are going to study are going to be um, traveling in homogeneous lossless medium with epsilon and mu parameters. And that wave is not having any components along the z direction, and it is not varying along z, I mean x and y directions. So those are the basic understanding regarding the assumptions under which we are studying the uniform plane waves. The uniform plane waves that we are studying and are studied under these two assumptions. Okay, so we are then going to study the properties of the uniform plane waves. Okay, and then once I need to discuss about something, I will come back to that mathematical derivation. Okay, so some mathematical derivations are required to analyze the properties of the uniform plane waves. Okay, so once I discuss that, I will get back to the mathematical wave equation that we discussed earlier. So until then, I think I will discuss the main parameters of the uniform plane waves. So properties of uniform plane waves. Okay, so there are mainly, I mean, I'm going to discuss mainly 5 parameters. Okay, so the first parameter, property, sorry, there are mainly many properties for uniform plane waves. So the first property that I'm going to discuss is the property that says that the electric field and magnetic field uh, do not have any components along the direction of the propagation. Okay, so okay, so I mean electric field and magnetic field uh, mm, components are only I will write it in a different manner, right? So there are no electric field and magnetic components in the direction of propagation. No electric and magnetic field components along the direction of propagation. So visually, what we mean by that is that now we are considering a plane wave, right? So the electric field and magnetic field that are generated on the xy plane are only along the xy plane. The components of the electric and magnetic fields are only along the xy plane. The components of electric field and magnetic field will not be along the z axis, right? The the electric field and magnetic field is propagating like this along the z axis, but uh, parts of the electric field are not along the z axis, okay, and parts of magnetic field are not along the z axis. They are along their own, I mean, directions on the xy plane. Okay, so I hope it is clear to you. It can be shown mathematically, right? It can be shown mathematically, but I don't know whether I'm going to take a lot of my time to show that. However, like you can do it by using the wave equation that we derived earlier. So the wave equation that we derived using our earlier, I mean, during our earlier lectures was this equation. Okay. So specifically now, right? So this is the equation. I will remove mu naught epsilon naught, right? We can consider for a medium of mu and epsilon parameters. So this is the equation that we derived earlier. Okay, so now I'm going to consider the electric field which is varying along Z and T only. Okay, so I'm going to consider electric field which is varying along Z and T only, right? And in that case, and if I further simplify this expression, which is the Laplacian function, okay, this is the Laplacian function, right? So if I expand this, I can write it as w squared w x squared plus w squared w y squared plus w squared w z squared into E Zt equals mu E and w squared over w t squared E Zt. So this is the behavior of the electric field uh, uh, component uh, once it is propagating uh, as a uniform plane wave, and this is the assumption that we made, right? So the electric field is only varying along Z and T. So if that is the assumption, then we know that the derivation with respect to x and y should be 0. Okay, so once we take that into account, we can see that the way the equation will be like simplified like this. Okay, so this is a simplified version of the wave equation, right? so in this case we are considering the electric field is varying along Z and T parameters. So once we take this equation into account, the solution for this equation is of the form, right? The solution of this equation we need to find in order to prove that the solution for this equation is not along the um, z-axis direction. The component of the electric field is not along the z-axis. To do that, we need to find the solution to this equation. Okay, so the solution to that equation will be of the form Ex is at t equals Ex plus, okay, cos omega t minus kz plus Ex minus cos omega t plus kz. Okay, this is the solution of this kind of equation, and this solution that we obtain shows the addition of two waves. This first part is the forward wave. The first part is the forward wave. The second part is the backward wave. Right? So there could be forward and backward waves that can occur in this system. Okay, so when we are considering our system, we are only going to consider the forward wave. We are only going to consider about the forward wave, because we are not going to consider about the reflections that can happen. And if we consider reflections that can happen, then we have to consider both the forward wave and the backward wave. But in this scenario, since we are considering the most simplest wave propagation, we are only going to consider the forward wave. And the forward wave is of this form. Forward wave is of this form. Right? So the forward wave, once we take it into consideration, right? A forward wave is denoted by Ex plus. So this plus sign shows that it is the forward wave. It is depending on Z and T, I mean coordinates, and it's behaving like this, right? So this is the forward wave, which is the wave that shows us the variation of the electric field, right? So this is the component. Apart from that, we can um, we can get the solution. We can get the get uh, uh, yeah. So this is the solution for the electric field, and we can use this equation for uh, multiple derivations. However, from this equation, we can actually derive the fact that the component, the electric field and magnetic field components along the z-axis is zero, right? So we need to do some more mathematical derivations to find that. So, however, um, we can actually do that. Right? So I will follow the most easiest way. So we need to show this equation in terms of phasor domain representations. So if I'm going to show this as a phasor domain representation, then I can write it as the real part of the Ex is at t. Sorry, real part of uh, real part of Ex is at t into Wait. So if I'm going to write it as the phasor domain, I can write it as Ex Ej omega t. Okay. And I can write the variation of the electric field along the Z direction, and I can uh, push the variation along the time direction into the radian or the polar, I mean, part of the phasor. So the the angle part of the uh, phasor representation. So with this, I can represent the phasor domain representation. This is the phasor domain representation. So anyway, using this, I can show that once I take the derivations along both sides with respect to time, derivation with respect to time on both sides will give me the result that W t is equal to j omega, right? And if I take the derivation with respect to z on both sides, right? This is actually wrong, right? I think you also must have seen it, right? So if I want to obtain this expression, I need to get this as the phasor domain representation, right? I denote the electric field components amplitude in here. Rest of the variations along the time axis and z axis I push into the angle part of the phasor. And then I take the real part of that, and then I can denote the electric field according to that. Okay. So actually I have to so I have I have to write it like this. Okay, because the variation of z and time are already included inside this cost function. Because of that, only the magnitude of the electric field need to be mentioned outside the cost function. The variations of the along the time and the z axis are already mentioned inside the brackets. Okay, so therefore the phasor domain representation will be like this. And then once I take the derivation with respect to time on both sides, I get this result W t equals j omega. If I take the derivation with respect to z on both sides, I get jk minus jk as the result. So using these results, I can simplify the wave equation such that the this wave equation that I used earlier can be uh, simplified into a form that shows me that the solution for the right. So this is the wave equation that we used earlier. So in here, rather than using this W t, I'm going to substitute j omega in place of W t, right? And then I'm going to rewrite this equation as once I take the Laplacian to one side, I can write like this, right? So the solution to this equation will be that the um, components of the electric field along the z direction will be zero. Okay. Uh, so the solution to this will be the component of electric field along Z axis will be 0. Okay, so once we take this equation into account, we can see that in order to find a solution, we need to have either the electric field part 0, right? So if the electric field part Ex is a T is 0, that is showing me that the magnitude of electric field along the Z axis is 0, right? So whatever it says, what it says basically is that there's no electric field component along the direction of the wave propagation. So if the wave is propagating along Z direction, there's no electric field along the wave propagation. There's no magnetic field along the wave propagation. So that is what we tried to show using this derivation. So finally, after coming to this after coming to this final equation, we can show that the solution to the electric field has no component along the wave propagation. And also this equation that we have derived here, right? This equation that we have derived here is known as the Helmholtz equation. This is known as the Helmholtz equation, right? So the equation that we derived there is known as the Helmholtz equation. And it's a popular equation, right? It is a popular equation, and it is an equation which shows us that there's no explicit time dependency, with ENH do not have explicit time dependency with wave propagation. Okay, so that means that yeah, there is a representation of time in this expression, but the electric and magnetic fields uh, do not have right. So earlier in the wave equation, we had an equation like this. Hello. So in uh, the wave equation earlier, we had this time dependent time dependent equation where uh, we had the operations basically showing us the time dependency. So this part shows us there's some time dependency on the variation of the electric field along the Z and T directions. However, like in this equation, once I take this equation, right? So without regarding this parameter, this is some input data that we put into the equation, right? So if I take the function of this equation, the operation of this equation, this operation does not have any explicit time dependency. Does not have any explicit time dependency. Time dependency. Okay, so the operation does not have any explicit time dependency. In here, the operation has explicit time dependency. Right, I hope it is clear to you. So the Helmholtz equation is useful in situations where we do not want to consider the time variations and its effect on the electric field. And once we want to investigate that, we use the wave equation. Okay, so this is the wave equation, and the above one is the Helmholtz equation. Okay, so the Helmholtz equation, once I take into consideration the using similarity, we can derive a similar equation for the magnetic field also. Right, so the magnetic field components also we can derive a similar equation. Right, I will take Hy is at T equals 0. Okay, so this is the type of the Helmholtz equation for the magnetic field. Right, this is the equation for the magnetic field. Right, so so uh, you might need to understand how to derive these equations. Okay, so with all that, I tried to show the uh, property that the electric field and magnetic fields do not vary along the wave of propagation. Okay, so that is the first thing. Second thing is that electric field and magnetic field are propagating in perpendicular directions. Right, so right, E and H propagate perpendicular to each other. Okay, so there there are electric field and magnetic field components in the plane that we considered. Okay, so we consider the plane, right? And then the electric field and magnetic field components can be in certain directions. So the main or the sum electric field that we have in a certain direction is perpendicular to the direction of the magnetic field. So all the time this rule is available, and we can show it mathematically using the equation for the Faraday's law, right? We can mathematically show that using the Faraday's law. So Faraday's law says that the curl of E is equal to minus dabba B over dabba T. So if I am going to solve this further, I can actually, uh, write this as minus J, right? So in here, I can simplify this equation by substituting instead of dabba over dabba T, J omega. And then instead of B, I'm going to substitute mu H, right? So with all that, I'm going to write this equation as minus J omega mu H. So the cross product of E is equal to this. And now what I want to do is I want to find the direction of the magnetic field with respect to electric field and so on. Because of that, I want to take magnetic field as a subject. Then I'm going to leave the cross product on one side, and I'm going to bring the j omega mu onto the other side. If I'm going to solve this further, I will be left with some calculations, and then I will be able to show that this H field is depending on the y axis. Okay, so I will leave, I can show this simplifications, right? So the this curl function that I take here can be found using the curl function. Okay, the determinant function. So the determinant function can be written like this, right? X hat, I can write it like dabba over dabba x, then dabba over dabba y, dabba over dabba z, and then ex component will be only, let's say it's only along the x-axis, and then if it is that, then the components along other directions will be 0. Well, once I solve this, I will be left with ex dabba over uh, dabba z, dabba over dabba z ex into y hat. This is what I'm left alone with. And since I can substitute minus jk into this, I am going to get plus jk ex and y hat to this as the answer. So therefore, I'm going to be left with minus jk ex y hat, and on the denominator, I'm going to write j omega mu. So with that, I'm going to be left with, since there's a minus sign here, I'm going to substitute that also, and in here, I'm going to have two minus signs, and because of that, the final result will be plus, and I will be having k ex y hat divided by mu omega, right? Mu and omega. This is the equation of magnetic field. So this is y hat. So when E is in the x hat, when E is in the x hat direction, so if there's any problem, please let me know. If you cannot hear properly, you can let me know. I will try to repeat what I have said. And then I have the third property of the uniform plane waves, which is regarding the wave impedance or the intrinsic impedance. Okay, so the wave impedance or the intrinsic impedance means how much of a impedance or how much of a resistance that exists to this propagation of the wave in the a certain medium, right? So once a wave is propagating, there's some resistance from the medium to the wave that is propagated, or the wave propagation, right? So there's some resistance to the wave propagation. So that resistance is defined by the medium that causes it. So that resistance is what we call as intrinsic impedance. The intrinsic impedance is denoted by eta, and it can be found by taking the ratio between the electric field and the magnetic fields, right? So by taking the ratio of the electric field and the magnetic field, I can take the uh, expression for the intrinsic impedance, right? So I will show you how to get that. So earlier we discussed about the situation where the electric field and magnetic field were perpendicular to each other. In that case, we were able to derive this equation, right? So K over right? I hope it is clear or you can remember. Okay, so we were able to generate an equation like this, right? Which showed us that the direction of the the magnetic field is along the y hat direction, right? So this we derived in the previous uh, property. So in that case, now we are able to, right? Now, since I'm going to represent this as a vector, I'm not going to put the y hat component, right? So since it's a vector, I know it has a uh, certain, I mean, I can put it here. Anyway, it won't like change our derivations. So I will keep it there because I want to show the direction of the magnetic field. And now I want to take the ratio between electric field and magnetic fields. So once I do that, I can take omega mu over k onto the other side, and then I can be left with, uh, right? I can be left with this, right? If I take the magnitude only, right? So considering the magnitude only, I can take this. So by taking the magnitude only, I will be removing the effect of y hat. So then I'm left with this, right? So another thing that we can observe here is the unit of this ratio, right? So if I take the units of the electric field, it would be volts per meter. The units of magnetic field will be amperes per meter, right? So once I take the ratio between those two parameters, I'm left with ohms, right? So because of that, the final result that we get for the ratio between the electric field and the magnetic field is actually an impedance. So because of this is known as the characteristic impedance or the wave impedance to the wave propagation. Okay, so this value is the impedance value actually. Okay, so because of that, its output should be given in ohms, right? So if we consider the, I mean, free space, we can find the value of the intrinsic impedance, right? If we consider the free space, the value of the intrinsic impedance, which we can denote using eta, we will denote as eta naught since it's a free space, and we will denote it as uh, omega mu naught over k, right? So since we are describing about the free space, I can further write this as now k value. Right? K value is something that we need to define further. Okay, so k value is something that we call as the wave number. Okay, so I need to now explain about the k parameter in order to further progress with this equation. So k number, k is wave number. Okay, so k is denoted or defined as the wave number. So it is defined as the rate at which the phase of the wave is changing. The phase of the wave is changing. Okay, so okay, so this can be mathematically shown as using 2 pi over lambda. Okay, so the amount of phase that is changed per unit length. Okay, that will give us the rate at which the phase is changing. Okay, so this is the wavelength, right? Per each, unit length, how much of a phase is changing, right? So that is basically what we are trying to calculate using wave number. Okay, and its units will be given as radians per meters. Okay, another way that we define the wave number is where we define the Helmholtz equation, right? So Helmholtz equation we defined like this earlier, right? So we defined it as like this earlier. Okay, so in that equation, this expression is known as the wave number. Okay, so this entire thing is equated to K. So K is defined as mu epsilon and omega squared. So this is another way of defining the wave number, the second method, right? So the second method, let's say. This is the first method of denoting the wave number or defining the wave number. Right? So in both the cases, we get the same result, right? So the reason is the lambda value varies with the medium and the frequency of the wave propagation. And in here also, the second equation also, the mu epsilon values change with uh, the medium, and the omega value changes with the frequency of the wave. So by taking the effect of the medium and the frequency of the propagation, the value of K will be same once we use both the first equation and the second equation. So anyway, K value is defined using these two equations, right? So we can substitute this second equation into this equation that we were solving earlier, and then we can substitute the uh, omega mu, mu, right? So I'm substituting mu naught epsilon naught because I'm going to be considering free space. And by that, I can cancel out the effect of mu naught, and I'm left with now, sorry, this is, sorry, this, sorry. So this wave number squared is equal to this expression. Okay, so mathematically it is defined that this mu epsilon omega squared is equal to the wave numbers squared. So this k squared is equal to this. Therefore, this should be square root and this should be just omega. Therefore, we can cancel out the effect of omega on both numerator and denominator, and we are left with this mu naught over epsilon naught as the result. So the neta or eta that we take as the intrinsic impedance will be equal to mu naught over epsilon naught square root. So this is the free space intrinsic impedance. Normally that value will be equal to 120 pi or 377 ohms approximately, right? So we can denote the impedance in terms of pi, or we can take the value of the impedance in using by substituting the value of pi into this and finding the final value. Anyway, basically the intrinsic impedance is about 377 ohms, and once we consider other mediums, then the value of intrinsic impedance will vary based on that medium. So if we want to find the intrinsic impedance of another medium, we need to substitute the values of the medium's parameters to find the value of the intrinsic impedance. So if we have a medium with epsilon r and mu r as the epsilon and mu values, then what happens is that the value of eta will be equal to mu r mu naught divided by epsilon r epsilon naught, right? So this is going to be the equation when we consider another medium with the relative permittivity epsilon r and relative permeability mu r. So then we are left with eta naught and mu r over epsilon r. So so this is how we can find the intrinsic impedance of any medium. Right? If the medium does not have any magnetic properties, then the value of mu r will be 1. And that is the case. If that is the case, the value of eta will be eta naught over the square root of epsilon r. Right? This is the equation for situations when the medium is not magnetic, right? And only the epsilon r permittivity value is changing with the medium. So this is just an equation that you can use if this is if this medium is specifically not magnetic. So in that specific case only we can use this equation, right? So it's better to use this general equation anytime you want, where you want to find the intrinsic impedance. So after that, I have the fourth property of the wave, the uniform plane waves. The fourth property gives us the property that the E and H, or the E cross H, gives us the wave propagation direction. Gives us the direction of the wave propagation. Gives the wave direction of wave propagation. So what do I mean by that? So electric field and magnetic field can be in uh, perpendicular directions, right? So we learned about that in the previous property. So we know that electric field and magnetic field are always perpendicular to each other, right? When we are considering uniform plane waves. And then in situations where we have the electric field and magnetic field in these two directions, we can show that the direction of the wave propagation is taken by the cross product between E and H. So the now E and H are along these two directions, and if I want to find the direction of the wave propagating, I need to use the right hand rule, right? So I need to use the right hand rule to find the direction of wave propagation. So the once I turn my fingers along the direction from E to H, right? Once I turn my fingers from E to H using the right hand rule, then I can show that the wave is propagating in this direction, along the Z direction. And if I have, for example, E and H in these directions, then I know the electric field will be generated along the vertically upwards direction. My fingers will be, curled in this direction, and my thumb will point in the vertically upward direction. So the direction of my thumb will give me the direction of the wave propagation. Okay, so with that I can find the direction of the wave propagation. Then the velocity of the wave propagation I call as phase velocity, can be found using um, can be defined using some parameters of the wave, right? So the phase velocity we can define as the ratio between the displacement of the wave over the time. So the displacement of the wave, let's say it is dt1 divided by the time t1. So the displacement I can find using different methods. So one method is to multiply the omega or the angular frequency with the time t1 and divide by the wave number. The wave number is k, right? So once I divide and once I take the fraction like this, what I'm left with is actually, I mean, in the numerator, I'm left with some radian value, right? So this is some radian value. In the denominator, I have radian per meters, right? So because of this effect, the displacement value is taken to the numerator, and I'm left with T1 in the denominator. Because of that, I can find the the variation of the displacement per unit time. Okay, so in here I have seconds, right? So the unit of the time will be uh, in some seconds. So therefore, the final output of this fraction will be meters per second. So with that, I can find the equation or the value of the phase velocity. So the value of phase velocity basically can be found, therefore, by taking the ratio between the uh, angular velocity, angular frequency, and the wave number, angular frequency and the wave number. By taking the ratio between those two, I can find the wave velocity, right? And also, there's another equation that I can use to find the wave velocity. The second equation is by taking the similarity that we have between the wave equation and the physics equation for the wave, which we derived in the previous classes. So we showed that the velocity of a wave propagation should be 1 over square root mu epsilon, right? So with this, we can find the velocity of the wave. So this result we got earlier once we were discussing about the wave equation of the electric field, right? And once we compared that wave equation with the wave equation of the classical physics. So the wave equation of the classical physics is of this form, and that equation has the velocity of the wave in the denominator like this. And once I take the similarity, right? So this is the equation that we have in classical physics for the wave propagation. Okay, in here this parameter is the speed of the wave, right? So since these two equations are similar, like using similarity, I can take this parameter is similar to this parameter. I can take this parameter is similar to this parameter. So using this relationship, I can say that the velocity v is equal to 1 over square root mu e. Right? So this is the equation that we can define for the velocity or the phase velocity. So the phase velocity value can be found using this equation. Okay, so this is the second method. Let's say this is the second method, right? So we discussed about another method which we derived that the omega over k also gives us the phase velocity. So there are so that is the first method. This is the first method, and that one is the second method. So there are two methods to find the wave velocity. So that is regarding the properties of the uniform plane waves. So the properties of the uniform plane waves were basically defining the the features of the uniform plane wave, right? How the uniform plane waves, electric field and magnetic field components are varying, and uh, how and where in what direction the wave is propagating, and what is the impedance to the wave propagation, and what parameter what parameters are defining the intrinsic impedance to the wave propagation, and what is the direction of the wave propagation, right? The direction of the wave propagation we can find by taking the cross product between the electric field and the magnetic field. And then finally, the velocity of the wave propagation depend on the wave number and the angular frequency parameters. Also, we can use another equation to find that velocity. And those equations were defined based on the mu epsilon parameters. So basically, those are the properties of the uniform plane wave that I wanted to discuss. And those uh, uh, those those parameters, such as the velocity, intrinsic impedance, are useful to study the behavior of uniform plane waves, right? So in order to study the behavior of uniform plane waves, we need to use the parameters such as the velocity of the wave propagation, the intrinsic impedance of the wave propagation, intrinsic impedance of the wave propagation, the velocity, and the direction of the wave propagation. Uh, right? Those things are important for us to uh, find the behavior of the plane wave. So with that, I will be uh, ending the discussion regarding the uniform plane waves. If you have any questions, you can ask. Right? So at this point, I will mention something regarding the mid exam also. But I think I will first do the rest of the lecture and then I will explain that. Okay, at the end of the lecture, I will mention that. Okay, so I will continue regarding the wave propagation. So until now, we discussed about waves uh, that were having zero attenuation, right? So we considered that the wave attenuation, we consider scenarios where the wave attenuation is zero, right? However, in real situations, the attenuation is actually happening, right? In that case, we need to apply that effect into our mathematical models and our designs. So, however, the waves actually attenuate. The waves actually attenuate once really attenuate. So once we have a wave, its amplitude will get attenuated with the time due to the effects of the medium and other factors. So the there are some factors which define the attenuation of the wave, where we call that attenuation factor using the symbol alpha. Attenuation factor is given by the symbol alpha, and there are other two parameters like propagation constant and phase constant. Anyway, I think I will not uh, explain regarding those parameters. So basically, you just need to understand the attenuation process and how it happens. So attenuation is the reduction in the amplitude the amplitude and energy of a wave as it travels through a medium. Okay, so the attenuation is the reduction in the amplitude and thereby the reduction in the energy of a wave as it propagates through the space and through a certain medium. So some factors that cause attenuation are absorption, right? Absorption, scattering, reflection. Okay, so okay, so the absorption is the energy absorption. The energy absorption when encountering water, rock, when encountering water, rock, etc. So what we mean is that once a certain wave is propagating in a certain medium and then it hits a body of water or it hits a body of rock, then its attenuation will get reduced. So if it hits some kind of a mountain or something, the attenuation, the wave will attenuate and its amplitude will decrease significantly. There's some kind of obstacle in the way. So obstacles such as rocks and water are very good material that will attenuate the wave. So if because of this, once we are transmitting signals in the free space, the the range of the wave will reduce once we have obstacles like this. So if we transmit a signal from a certain base station, we transmit some signals from a certain base station and we have a mountain and water bodies in between, then our wave will hit this obstacle and will move in a certain other direction. Because of that, the wave will not come and reach our device. We will not get signal once we stay in a place where we have obstacle in between. So because of that, we need to again put some tower maybe on top of the mountain to reach the people who cannot be reached due to this obstacle. So likewise, absorption is one factor that causes attenuation of the wave. Scattering is another phenomena. Like scattering is defined as wave changing its direction and losing energy. Wave changing its direction and losing energy. Encountering medium such as soil and sand. So, if a wave is encountering soil and sand, for example, the wave will change its direction and the wave will scatter around that obstacle. So, part of the wave will like hit on a certain obstacle, and the part of the waves will scatter around that obstacle. There's some kind of obstacle. The part of the waves will be scattered around that obstacle. So, due to this scattering effect, the wave will not be able to go through the intended direction. The wave was intended to go in certain direction, but it won't go there now because of the scattering effect. And then we have the reflection. Reflection is defined as the uh, wave moving in the opposite direction, moving back into the same medium. And Okay, so what I mean is now in reflection, we hit some kind of a obstacle and part of the wave is getting reflected back. So the reflected wave will have a certain amplitude and pace, but there's some reflection uh, out of the incident wave. So there's some incident wave, it has some power, but part of that power, that energy, is getting reflected back once it hits a certain medium or some kind of a high obstacle. And so because of that, the reflection also reduces the amplitude of the wave. So reflection means change in the direction of the wave, change in the wave direction, and uh, moving back to the same medium, back to the same medium. So the phenomena of uh, coming back to the same medium after hitting a certain obstacle is known as reflection, right? So same medium, it is coming back to the same medium, right? So that those are basically the concepts that I wanted to discuss regarding the wave attenuation. If you have any questions, you can ask, right? So now I will explain to you regarding the mid exam, right? For you, right? So the mid exam, I'm hoping to hold on the Wednesday, this upcoming Wednesday, 19th of Wednesday, right? 19th of July, which is a Wednesday. Okay. So the midday exam will have questions, right? We'll have questions from the electric and magnetic fields, right? Electric and magnetic fields, electric field related concepts will be questioned, magnetic field, Maxwell's equations, and uniform plane waves. Okay, so these 4 sections will be questioned in the mid exam. So you need to prepare for these sections, right? So prepare likewise. And the exam will be held online for you, right? Held online. You need to prepare beforehand with the safe exam browser installed, right? Only the students who have that option enabled can uh, access the quiz, access the exam that I have uploaded to LMS, right? You need to download the exam, safe exam browser extension. Right, so this is, I think, having 260 something megabits of size, so it will take some time to download. So therefore, install it today itself or very earlier than the exam. Okay, so it takes some time to download this. So anyway, you need to download this and you need to be ready with this before coming to the exam. Okay, otherwise you won't be able to do it on time, and I will not allow you to write more than the 1 hour time duration. Okay, so therefore please be ready beforehand. So after you have downloaded this safe exam browser, you can open the configuration file that I give you, right? I will give you some configuration file. You can open that configuration file using the software that you have installed, right? So open the configuration file in the software, in the safe exam browser software, right? And then once you have opened that like that, only you can access the exam in the LMS. Okay, so after that you can do the exam for 1 hour, and then I will give you a password to exit the exam browser extension. And then using the password, you can exit the exam and you can leave the exam. That is how that's going to happen, right? So you have 1 hour you have where you have to write answers, right? The exam will be a closed book exam, right? This online exam, but I do not want you to refer any book. So you need to uh, keep your video camera on, right? Video camera on in your Zoom meeting, right? So therefore, be prepared for that. So I will be invigilating. You should do it with video camera on, and the exam will be closed book. Okay. So if you have any questions, you can ask. So do not ask me about the exam via phone call. So I mean, first you need to refer this lecture, then you can get all the information. Even after that, you have problem, you can email me. I will answer that, right?